Thank you. I'm impressed at how many people are awake at this hour of the morning, although I better not check in an hour to see whether that's still the case, but I'll try to keep this as lively as possible. So the work I'm going to be talking about was all, the part that's not review of other work is all done in collaboration with Stefan Hollins, and the details of the newest parts of the work are all in this paper that was posted on the archives that's to appear in Communications in Mathematical Physics. So I should begin by first saying what quantum field theory in curved space-time is. So it's simply a theory that we're seeking to formulate, where all the matter fields are treated fully in accord with the basic principles of quantum field theory. Now, what the basic principles of quantum field theory are is the main subject of the talk. But what I want to emphasize here is that gravity is being treated classically in accord with general relativity as a curved space-time metric. So there's no attempt being made to do a quantum theory of gravity. Gravity is basically treated as a background external field here. No one expects this to be an exact theory of nature, but I think it's reasonable to expect that it would be a good approximate description of nature in situations where you're away from Planck scales and quantum effects of gravity itself don't play a dominant role. And I think it's fair to say that even though it's treated gravity classically, probably some of the deepest insights that we presently have into the nature of quantum gravity itself come from the study of quantum field theory in curved space-time and effects like the Hawking effect and so on. But I won't be discussing anything related to quantum gravity. Gravity will be a fixed classical background in everything that I'll be saying from this point on. Well, my own interest in quantum field theory in curved space-time certainly started out with direct interest in the physical phenomena near black holes and early universe and so on, and my interest certainly remains there, but in trying to understand those phenomena better, one really needs to have a clearer formulation of what quantum field theory in curved space-time is. And for that, I think that leads to questions about what the essential elements of quantum field theory itself are, even in flat space-time. So if one is attempting to take what one knows in flat space-time and generalize it to curved space-time, then as I'll be describing much more explicitly very shortly, one notices that there are a lot of elements of quantum field theory the way it's usually formulated, whether in textbook non-rigorous treatments or, as I'll describe, Whiteman axioms or anything in between or to the sides of that. They contain many elements special to Minkowski space-time. But we're now in this room, space-time is curved, but we can certainly neglect that, treat it as nearly flat, and perhaps do some perturbative correction of quantum field theory in flat space-time and perfectly well get away with that. But the most interesting phenomena that one would hope to treat in this context would be things in the early universe or near black holes, where you certainly can't even approximate flat space-time as nearly flat. So one really wants a formulation of the theory that works in an arbitrary curved space-time, or at least an arbitrary globally hyperbolic curved space-time, so that there aren't any causal pathologies, and classically one has deterministic behavior. Now, in classical field theory, one has in some sense the same issue of, we know Maxwell's equations very well in flat space-time, but we'd like to have them to, classical electromagnetic theory in flat space-time, we'd like to have that in curved space-time. There isn't a big fuss made over how to generalize classical field theories from flat to curved space-time because it's basically quite easy and straightforward to do, at least once you're in the swing of general relativity and curved space-time. I claim that that's because there's really, in the classical formulations of classical field theory, a completely clean separation between field equations and solutions. Right? We've got Maxwell's equations, we've got solutions to Maxwell's equations. The idea or the point is that field equations can quite straightforwardly be generalized to curved space-time in a completely local covariant manner that's entirely satisfactory. If you want to generalize solutions from flat to curved space-time, you've got a big problem because there's not necessarily any correspondence between solutions. I don't know what a plane wave in some space-time with no symmetries that's not asymptotically flat is supposed to be. I wouldn't know how to formulate that, but I don't need to, because for the formulation of the theory, I just have to say what the generalization of the equations are, and I'm done. I mean, of course, there's a lot of work to be done in solving those equations in a curved space-time of interest, but those are more practical problems. The formulation of the theory is clear. Now, in quantum field theory, I would argue that states are very much the analog of solutions in classical field theory, but in the formulation of quantum field theory as opposed to classical field theory, properties of states are very deeply embedded in the formulation of the theory. Maybe the most clear example of that is the existence of a Poincare invariant vacuum state. Well, if you're in some curved space-time with no symmetries, and you have to generalize this notion to that curved space-time to formulate the theory, I would claim you're in a lot of trouble. So for this reason and for other reasons that I will get into, it is not at all straightforward to take quantum field theory as usually formulated in flat space-time and reformulate that in curved space-time. And now let me get into more of the details of that, or be much more explicit about that by taking an explicit look at Whiteman axioms in Minkowski space-time. I've just chosen this because it's a clear, clean set of basic principles of quantum field theory, but again, any other formulation, I'd have very similar things to say. So I've listed here, just copied straight out of Streeter and Whiteman, the Whiteman axioms, which, well, you can probably read for yourself, but I mean, it starts out with states arrays in a Hilbert space, and that Hilbert space carries a representation of the Poincare group. Then we have the spectrum condition that was mentioned in a number of talks here the last couple of days that basically say that total energy is positive, or total form momentum is time-like or null. Then we have this condition that I've already alluded to, that we have some unique Poincare invariant state. Then we have a statement that we've got the quantum fields are represented as operator value distributions on a dense domain. Okay, that's not too bad, but is Poincare invariant as well as invariant under the action of fields in their adjoints. Then we've got fields transform in a covariant manner under Poincare transformations, and then we have a statement that quantum fields commute or anti-commute at space-like separations. So you might say, what's the problem with these in curved space-time? Well, much easier question to answer is what's okay with these in curved space-time. That's a really short list. What the problems are is practically everything. So one of the most obvious ones is that generic curved space-time won't have any symmetries at all. So you're certainly not going to require Poincare invariance, but you're also not going to have, in general, any other. I mean, if you wanted to do quantum field theory in de Sitter space-time, you could impose de Sitter invariance in a similar way and perhaps proceed. But if you want to do a general curved space-time with no symmetries, there's no invariance or covariance of under any kind of space-time symmetry. So everywhere the word Poincare invariant was used, there's a problem. There's also a problem where the word Hilbert space was used, as appeared in several places. Even if you go to the case of free fields, which one does have a good, clear understanding of, if you consider them in spacetimes with non-compact Cauchy surfaces, there are plenty of, infinitely many, obviously, unitarily inequivalent Hilbert space constructions of free quantum fields. Well, there is in flat spacetime as well, but the Poincare symmetry and the presence of a Poincare invariant state in one of these representations can be used to pick out a preferred representation that one can just declare to be the Hilbert space and so on. But in again, a general curved space-time in the absence of symmetries with a non-compact Cauchy surface, none of these, there doesn't appear to be any one representation that's preferred over the others. The Poincare invariant vacuum state axiom is in Poincare invariance was already in a lot of trouble as I've described here, but even picking out some preferred choice of vacuum state is a problem, as a major problem, as I'll elucidate further in a few minutes. And then in the spectrum condition, as I'll say a few words about very shortly, I claim there's no analog of the spectrum condition in a general curved space-time without any time translation symmetry that could be formulated in terms of total energy momentum of the quantum field. Well, even with time translation symmetry, you'd have a problem. So if you ask what's the situation with the Whiteman axioms, every one of these has a very serious problem except the last. Space-like separations are just as well defined in curved as in flat space-time, and you can impose this condition with no problems. But nothing else, I claim, generalizes straightforwardly. So let me say a few more words about what the problems and issues are. So say a few things about the spectrum condition. So first of all, in classical field theory, one has a stress energy tensor. One has conservation of the stress energy tensor, but what's interesting in general relativity is the conservation of stress energy, this local kind of conservation of stress energy law expressed in this manner doesn't lead to a global conservation of energy unless you have a time translation symmetry. Well, more generally, if you have any vector field that you're going to take as the generator of time translations, even if it's not a symmetry, it's natural to define total energy at some time sigma corresponding to some Cauchy surface by doing this integral over space-time. For physically reasonable fields, the dominant energy condition holds, which guarantees the positivity of the integrand. And so classically, you have positivity of energy, but you don't have, unless this T is a symmetry, which you won't have in general, you don't have any global conservation law of energy associated with that. If we move over now to quantum field theory, I think there's every reason to expect the smeared stress energy tensor smeared in with some test distribution will be well defined, and I think there's every reason to expect that it can be defined in such a way as to be conserved. But now since we have to do the space-time smearing, it was really the conservation of energy that allows one to define energy at a sharp moment of time, because it doesn't really matter if you smear over time, it doesn't change the value of energy. So we wouldn't expect to have an energy defined at a sharp moment of time. Much more significantly, as is well known, the stress energy operator won't satisfy any energy conditions at all. One would be able to find states where point-wise this can in fact be made arbitrarily negative at those points. And in a curved space, that's true in flat space-time as well, but in flat space-time the integral will still be positive. But in a curved space-time, there's no reason to expect E to be positive. And indeed, there are simple examples of, for example, just in a 1 + 1 dimensional space-time with the spatial dimension made into a circle, you get Casimir-like negative energies in the ground state of the field, and you don't get positive energies. So I claim that there doesn't appear to be any way of generalizing the usual flat space-time spectrum condition to curved space-time in terms of stating the positivity of something representing total energy. There are energy inequalities that allow one to put lower bounds on E, at least over time-like curves or things like that, smeared over, but one shouldn't expect to get any good way of generalizing the spectrum condition in this kind of global way. Let me make a few comments now on this lack of a preferred vacuum state of any kind, and for that matter, notion of particles. And again, let's start with the free field in Minkowski space-time. I claim if you look at the standard notions of particles, vacuum, and so on for a free field, that is intimately related to the notion of positive frequency solutions of the classical field equations, but this notion of positive frequency solutions very much depends on the existence of a time translation symmetry. So if you want to generalize these notions to curved space-time, well, if you have a stationary curved space-time, it's straightforward, basically, to generalize these notions and define some notion of a vacuum and particles for a free field. But if you're talking about curved space-times with no time translation symmetry, then there's no obvious way of doing it. The problem is that there's no way of doing it, there are just many ways of doing it, and none of them seem preferred. One can pick out a kind of class of states that are vacuum-like in character, namely the quasi-free states that have, the correlation function satisfying, again, I'm talking in the free field context, satisfying the same relations as in the usual vacuum state. But there are lots of quasi-free states. And one has the notion of a Hadamard state, for which the singularity of the two-point function of the field is, as the points come together, is like that in flat space-time. So one can demand these properties to characterize a vacuum state, and once you've chosen one of these, you'd have a corresponding notion of particles, but the problem is there are lots and lots of quasi-free Hadamard states in a curved space-time, and in the absence of some symmetry, none of them appears preferred. Even worse, as I've already indicated, if you have non-compact Cauchy surfaces, in the case where you have compact Cauchy surfaces, all of the Fock representations that you get by choosing different quasi-free Hadamard states lead to the same representation. But in the case with a non-compact Cauchy surface, that's not true, and you get unitarily inequivalent Hilbert space constructions of the theory. So there's not only is there not a unique vacuum state, there's not a unique Hilbert space that one can pick out by any criteria that seem reasonable in the absence of symmetries. So to me, at least, my own reaction is that the situation with respect to seeking a preferred vacuum state is really a lot like the situation in classical general relativity of at least students learning general relativity for the first time who've learned special relativity in terms of global inertial coordinates would like to know okay, if you're not in flat space-time, what is the analog of global inertial coordinates and what preferred coordinate system should you use? Well, I think it's safe to say now that more than 90 years has passed since the formulation of the theory, and no one has come up with a useful notion of a preferred coordinate system. In fact, there are theorems that you can't globally over all space-times choose consistently some preferred coordinate system. But anyway, even if one could, it's not particularly useful. It's much better to formulate the theory geometrically and not have to specify some choice of coordinate system to formulate the theory. My feeling is that although only about 40 years has passed with people trying to do the same kind of thing in curved space-time, I think it's reasonable to conclude that it's fruitless to look for a preferred vacuum state in general space-times, and indeed, it's best to formulate the theory in terms of an algebra of local field observables where you don't have to introduce a state or representation at the outset to formulate the theory. You have the formulation of the theory with the specification of the algebra of local field observables. Okay, well now with a little bit, having indicated some of the difficulties, let me now talk about overcoming the difficulties, which will be the rest of the subject of the rest of the talk. So one of the difficulties, the one with the word Hilbert space and the fact that there are these unitarily inequivalent constructions, is very nicely and simply overcome, as I've already indicated, by simply taking the algebraic approach to formulate the theory, to formulate the, state what the algebra of observables is, rather than stating what the Hilbert space is and what operators on the Hilbert space are, what action they have, formulated in the algebraic way. And, since one is getting away, as I've already indicated, from any notion of particles, any notion of S matrix, etc., in the curved space-time context, the algebraic approach really also is extremely compatible with the idea that the fundamental observables are the quantum fields themselves that make up, at least in the viewpoint that I'm taking, the algebra that one is working with. I think it would be fair to say that had the algebraic approach not been formulated 50 years ago or so for other reasons in flat space-time, I would think it would have been formulated in curved space-time just to deal with this issue of there just doesn't seem to be any preferred Hilbert space construction of the theory. I'm not saying all of the machinery would have been developed, but the basic concept that one wants to formulate the theory in this way. The difficulties that I alluded to with the spectrum condition can be very nicely overcome by formulating the spectrum condition in a completely local way as a microlocal spectrum condition that restricts singularity structure. I'll just say a few quick words about that in a moment for people who are not familiar with that at all, but I won't describe this in detail. And finally, well, not finally, because there's one more condition that we'll have to deal with, but many aspects, but not all of them, not Poincare invariance of a vacuum state, but basically the other places where Poincare invariance or covariance are used can be very nicely replaced by a requirement that quantum fields be local and covariant. I don't mean here that they're constructed out of the metric that you make the fields out of the metric, but that you use only the metric in a local and covariant way in the construction of the quantum field theory. I'll explain what that is, what I mean by all this in a moment. So Just to say a few words, because this is a major advance in the subject in the last 15 years, just to say a few words about what this is and how one solves the problem of formulating a spectrum condition. Well, the idea is to use microlocal analysis techniques. Basically, if you have a distribution and multiply it by some function of compact support near x, so that you kind of localize it near x and look at the decay properties of the Fourier transform and look at properties that hold no matter how small the support of the test function near x that you've multiplied the distribution by are. You can thereby, by looking at the decay properties of the Fourier transform, get a notion not just of the points at which a distribution is singular, but the directions in the cotangent bundle, because the Fourier transform variable is most naturally thought of as a vector in the cotangent space. So you can get a notion of the singularities of a distribution in phase space, not just in position space. That's called the wavefront set. And that really provides an ideal way of characterizing singular behavior of the distributions that you get by applying a state to a product of fields, because it allows one to describe a kind of locally positive frequency character to the singularity structure of this distribution that captures the notion that positive frequencies are really underlying all of this, even though there's no global notion of Fourier transform in the space-time. One has no global notion of positive, even in the free field case, of positive frequency solutions, anything like that, but you can still talk about the singularities of the, in particular, endpoint distributions of being of this positive frequency type. So that allows one to formulate spectrum conditions by demanding that the wavefront set of this distribution lie in a certain subspace of the cotangent bundle that satisfactorily replaces this spectrum condition. The concept that allows one to find an adequate replacement for a very satisfactory replacement for most aspects of Poincare invariance and covariance is this notion that the quantum fields be local and covariant. And the idea, as I've already indicated, is we want the construction of the quantum field theory to depend, quantum field theories in different curved space-time are different theories, but we want the construction of the theory to depend on the space-time metric only in a local and covariant way. Well, so what I'm going to do now is explain how to formulate that kind of notion. The first thing to notice is that if you're going to formulate that kind of notion, you better not just try to formulate your quantum field theory in one or some highly restricted class of curved spacetimes. It would be best to formulate the theory in all globally hyperbolic curved spacetimes, because what I want to say, or the way that this notion would be formulated, is that if we're trying to look at what the quantum field algebra is localized near point x, if we vary the metric in some arbitrary way away from point x, nothing happens to the local algebra near x. That's, I would claim, the key idea of this condition. But if we're going to be saying that nothing happens when we make these arbitrary variations, we better have the theory formulated in all, or an extremely wide class at least, of curved space-times. So how does one formulate this kind of notion? Well, suppose that you have a space-time that in fact, can be isometrically embedded into some open region of some other space-time in a way that preserves all of the causal relations. That is, all of the causal relations between events here in this space-time are the same as here, right? If you could have a situation where you took this and embedded it in such a way that it kind of curved around and came back near itself, and you'd have other ways of getting within this space-time between 2 points here and here than you had over here. But if we have a causality preserving isometric embedding, then what we want to say is that this embedding always induces a natural isomorphism of the quantum field algebra that you had here into the quantum field algebra associated with this local region here in this space-time. That's the idea that despite the fact that we've got lots more stuff going on here, the theory didn't change. We further want to demand that under this isomorphism of the algebras, I mean the algebras are, I'm assuming, are being generated by quantum fields, we want this isomorphism to take the quantum field that we called phi of f, over, gone back too far. Yeah, we want the quantum field that we called phi of f over here to be carried into the quantum field with the same label, but with the test function being the push forward of the test function that we were smearing in with here. So I claim that is, this basic idea is formulating the idea that the quantum field construction is local and covariant in the space-time metric. Now, that's a condition that might sound reasonable to impose. What might be harder and hardest to understand is what in the world does this have to do with Poincare covariance? Well, that I think can be seen by taking a particular example of this, where this space-time is Minkowski space-time, this space-time is Minkowski space-time, the region O prime is all of the space-time, and this isometric embedding is a proper Poincare transformation. Then this condition gives you an isomorphism of the field algebra now to itself associated with every Poincare group element. So it gives you an action of the Poincare group on the field algebra, and this condition on the quantum fields tells you that the quantum fields themselves transform covariantly under the Poincare transformations. So the imposition of this local and covariant condition contains, is a condition that when specialized to the Minkowski space-time example can be seen to contain much of the essential ingredients of Poincare invariance and Poincare covariance of the fields, but now it's been formulated without making any reference to symmetries in the context of a general curved space-time, and it has the same power that requirements of Poincare invariance and covariance do, but without any need for symmetries. So it's now time to take stock of things and see how we're doing in generalizing the Whiteman axioms to curved space-time. So I've repeated the Whiteman axioms in black here. There was a problem here with Hilbert space and Poincare group, but if you formulate the theory in the algebraic approach and impose this local and covariant field condition, that's a completely adequate replacement for this first axiom. Then we had the spectrum condition, and that's completely, which is hopeless, I claim, as a global condition to generalize, but that's very nicely replaced by the microlocal spectrum condition. we had a condition of there's a unique Poincare invariant state, the vacuum state. That's in red because I haven't said anything yet to generalize that. That's a real problem still, given what I've said. But the rest of things are fine. This stuff with the dense domain and the Poincare invariance of the domain is fully adequately replaced by just doing the, given a state of the GNS construction and the algebraic approach, that will automatically give you this kind of dense domain that's invariant under the fields and their adjoints, and the local and covariant field condition will give you the Poincare invariant part of that, or will give you a condition that adequately replaces the Poincare invariant part of that. The fields transform in a covariant manner is adequately, fully satisfactorily replaced by the local and covariant field condition. And the last axiom was the only one that was okay in the first place. So taking stock of things using the ideas that I've described so far that I would regard as fully well established and accepted by people, or I think not controversial at all. What leaves us, though, is the issue of what do we do in curved space-time to adequately replace the requirement that there be a Poincare invariant state? And this notion is used very critically in a lot of aspects of quantum field theory, in the proof of spin statistics theorem, PCT theorem, and so on. The existence of a Poincare invariant state plays a critical role. We can't just abandon this, or we'd lose a lot of the content of that we have in flat space-time quantum field theory. So the proposal that Stefan Hollins and I have is that, in fact, the appropriate replacement of this is something that has nothing to do really with states at all, or nothing to do with any kind of preferred states or anything like that, but that the appropriate replacement is to postulate that fields have an operator product expansion. Now, many people in this audience who know a lot more about operator product expansions than I do, but for the people who don't know anything about them, right, the simplest example of the kind of operator product expansion that I'm talking about here is what you'd have for, say, a Klein-Gordon field, well, in flat or in, I think I want to consider it in curved space-time. It's an asymptotic formula for the product of fields when the 2 points become close. The notion of a Hadamard state, I mean, one way of formulating it, the old way of formulating it, there are much nicer ways in terms of the wavefront set ideas, but the one way of formulating it is that as you bring the points close together, this goes, the singular part of this becomes some locally and covariantly constructed Hadamard distribution times the identity operator plus a remainder. The leading order term in the remainder actually provides you the definition of the Wick power phi squared, and other terms in this expansion, well, would, in the free field case, would just provide you, I guess, derivatives of phi squared. In fact, key point is that this is more singular than any of the other distributions. Well, the other distributions are not even singular at all in this case. So an operator product expansion for arbitrary products of fields, including these Wick powers or composite type fields, exists for free fields in curved space-time, and Hollins showed several years ago that it exists order by order in perturbation theory, at least for renormalizable interacting fields in curved space-time. One wouldn't expect an operator product expansion to exist for non-renormalizable theories, or theories that are not suitably free in the short distance limit. But our proposal is that this should be elevated to a fundamental status in the properties of quantum fields. And the key, well, there's more that I'll want to say about this in a minute, but the key motivation for that is that this appears to provide a completely adequate replacement for the existence of a Poincare invariant state. Again, you might wonder, what in the world does an operator product expansion have to do with the Poincare invariant state? Well, of course, it doesn't have anything to do with the Poincare invariant state, because we're not going to have anything like this in the quantum field theory. But the coefficients of the identity element in operator product expansions, I mean of arbitrary components, arbitrary products of fields, are going to play the kind of role in this formulation of the theory as vacuum expectation values play in Minkowski quantum field theory. So that's why I'm referring to it as a replacement of this condition. So our present viewpoint on quantum field theory is, well, we start with some background structure that I've been assuming all along of a space-time manifold, a space-time metric, and we also will have choices of time orientation, space-time orientation. If we're dealing with spinor fields, we'll have spin structure to deal with. And the idea is that for every choice of M, or every in a wide class like globally hyperbolic spacetimes, we're going to have some algebra of local, that's comprised by local field observables. Now, in usual approaches, one would normally assume that this contains, the algebra itself contains the full information about the quantum field theory. In our viewpoint, the algebra contains very little information. The information is actually going to be in the operator product expansion. The algebra will contain some information, but it's really information about relations between elements in the algebra that can be derived from the operator product expansion. So all of the non-trivial information about, in our viewpoint, about the quantum field theory should be, that distinguishes one theory from another, aside from the list of fields, would be, in our viewpoint, contained in an operator product expansion, by which we mean an asymptotic sort of formula for the product of fields in terms of distributions and one-point fields, where this formula is supposed to hold in a limit as all of the x's approach the point y. So the further axioms then of the theory, or the specification of the theory would consist of specifying the operator product expansion coefficients, and the axioms of the theory then from this point of view would be properties that the operator product expansion coefficients have to satisfy. I will not discuss this in a lot of detail. You can look at the paper that I referenced at the beginning to state these. This is the first 4 of the conditions. This has already basically been defined, and we want that to hold for these distributions. There are simple conditions involving the identity element and compatibility of the star operation. There are obvious causality conditions. I will explain a little bit about this dimension and scaling degree, because that will be needed to just explain how this gives rise possibly to relations in the algebra. There are spectrum conditions and so on. This associativity condition, that, as we call it, is a very important one, which again I won't be describing in detail, but the idea is that if you have a product of more than 2 fields, you could consider situations where you bring 2 or more of the points together closely first, and then the rest follow later. And you could then imagine you could have done an operator product expansion for the first group first, written it out in this kind of way and then done an operator product expansion, replaced 3 of these fields here with 1 point fields here, the associativity condition is just the statement that you'll get the same final answer if you do it in these different ways and use operator product expansion formulas in the intermediate steps going along. So it essentially reduces things down to knowing operator product expansion coefficients for 2-point distributions. Just so you have a little of the flavor of what we're doing or trying to do, I'll just mention these, the definition of the dimension and of the fields in our list of fields that generate the algebra, and a condition on the scaling degree of the distributions, just so that at least I'm saying something about what we're doing, and then I'll move on back to the more general ideas. So if we consider the operator product expansion of a field and its adjoint, well, if we single out the identity element in that expansion, we demand that the scaling degree of the coefficient of the identity be positive. In other words, this be singular. We use the scaling degree of the coefficient of the identity to define the dimension. And then we are basically required that all of the other coefficients not be more singular than this, well, taking into account what the dimension of these fields are. So the one of our conditions restricts the scaling degree of the other coefficients in terms of the dimensions of the fields that occur there, that basically guarantee that this be that there be no more term in the expansion more singular than the coefficient of the identity. Now, we get relations in the algebra, which might be things like field equations for the field. It might be other relations that occur for the fields. Those we arise, in our way of thinking about it, only from operator product expansion. Basically, if you can find some linear combination of fields such that when you formally perform the operator product expansion for this linear combination, if the if none of these terms are singular, then we declare this O to be 0, which gives a relation which might again be field equations. This list of fields includes, all composite fields as well. So there are nonlinear relations, of course, that can occur even though I've written this as a linear sum. So the algebra then is, in this view, is taken to be basically quite trivial. It's really taken to be just the free star algebra that we generate from the list of fields, but then we factor it by any relations that arise in the manner that I just described from the operator product expansion, and it's also factored by commutativity or anti-commutativity relations, but nothing else. The state space then is taken to be, as usual, a positive linear functions, but we also impose the microlocal spectrum condition on the states, and we, of course, demand that the distributions we get by applying the states satisfy the OPE relations. The point is that everything is then uniquely determined by the operator product expansion. Now, let me just back up and say, I mean, we were led to this proposal from, as I've described, the issue of how do you replace and get the content of Poincare invariant vacuum state in a general in the general curved space-time setting, and as I've explained, the coefficient, as I've indicated, I haven't explained, the coefficient of the identity appearing in an operator product expansion and its properties plays a lot of the role in arguments, spin statistics, PCT theorem, that the Poincare invariance of the vacuum state played in the Minkowski formulations of the theory. But the other reason why at least this is attractive, I like this proposal is that I don't see how one will easily get algebraic relations in the algebra that will be of this local and covariant character, unless, let me say it this way. If all of the non-trivial relations in the quantum field theory are derived from expressions of relations of this kind of form, the theory is going to be automatically local and covariant in its nature. And it's not obvious to me how to construct a theory that is of this local and covariant nature that I believe one needs without going to something that in essence is expressing point-like relations. Now, you'll never have ordinary point-like relations holding between fields, and operator product expansion is the closest thing that you can come to, I would argue, to having point-like relations between the quantum fields. And in our viewpoint, that is what is effectively providing all of the relations in the theory. So in terms of results, we've reproven the spin statistics theorem in this framework, largely by copying the Minkowski space-time proof. A little bit more interestingly, we can prove a version of the PCT theorem, but this has a very different character in the curved space-time context because we don't have parity and time reversal symmetry. So in fact, what the PCT theorem does is relate the algebra of observables and states in a background structure that consists of a space-time with a particular choice of time and space-time orientation with a corresponding background structure that's the same space-time as a manifold and metric, and the same in terms of the space-time orientation, but has the opposite choice of time orientation, and if we're dealing with spinor fields, has the corresponding choice of spin structure. The claim is that these algebras are then naturally antilinearly isomorphic, and we have a corresponding isomorphism of the state space in this case. So what this means is that the PCT theorem doesn't tell you about, if you're, let's say, in an expanding universe, it doesn't tell you that, relations with particles, if you've defined those, or at least, fields, are related to phenomena with the conjugate fields or whatever. It tells you that phenomena dealing with fields in an expanding universe are related to phenomena with the corresponding conjugate field in a contracting universe. It is because of the reversal of the time orientation, one is effectively dealing with a different space-time. The expanding and contracting universe space-time that I just alluded to are the same as manifold and metric, but have opposite choice of time orientation. Okay, so to conclude, let me comment on the outlook of this and reveal, some of my grand hopes that are still, very far from being realized in this, but it is something that I hope, will be able to gain some further evidence on as time goes on. So our attempt to formulate or generalize the formulation of quantum field theory to curved space-time, which was successful without a radical reformulation of the theory in terms of doing everything except this existence of a preferred vacuum state. To get this incorporated in some analog of this incorporated in the curved space-time has led us to a viewpoint where operator product expansion is elevated to a fundamental status. And in this viewpoint, then, the operator product expansion is what would contain the non-trivial information about a particular quantum field theory. What I very much like about this is that it really gives a perspective that's much closer to classical field theory, because the entire content of the theory is really expressed by local relationships satisfied by the fields. And I mean really local now. I mean, this is as local quantum physics as I think one can get, because these relations, although not exactly at a point, are arbitrarily close to a point. The key thing is that, I mean, we've succeeded at least to the level of giving a proposal that, that may have a chance of going somewhere, because we've completely gotten rid of any role of symmetries and preferred states in the formulation of the theory. And that's, I think, a very critical aspect. Now, on to the grand hopes. Of course, there's, it's extremely well known that perturbation theory in quantum field theory has major convergence problems. At least some of the convergence problems, and I'm wondering if perhaps not all of them, trace back to the fact that one has a vacuum state appearing in here, and that the vacuum state itself is clearly going to have a non-analytic dependence on coupling parameters. My hope is that by getting rid of the vacuum state or any other states in the formulation of the theory and working entirely with the operator product expansion coefficients, one might get around this major issue and difficulty. So let me illustrate that in the only good example that I have to illustrate this, which unfortunately is a free quantum field theory, but we can consider a massive quantum field theory with the mass squared being the parameter of the theory. So, of course, a vacuum state in this theory is, let's say in 4 dimensions, is only going to exist when m squared is greater than or equal to 0. And it's well known that this vacuum expectation value has this character as a function of m squared, and the log m squared that you see here is illustrative of the non-analytic behavior, and there'd probably be something wrong if this vacuum expectation value behaved analytically in m squared at m squared equals 0, because you'd be able to continue it to negative m squared, but there's no vacuum state at negative m squared, so something should be wrong. So vacuum expectation values and expectation values in physical states are going to have this non-analytic dependence, but the operator product expansion coefficient doesn't suffer from that, at least if it's defined properly. And I won't go into all of the reasons why it's really necessary to do this, but apart from trying to make something analytic in m squared, the claim is that to properly define the operator product expansion, one has to introduce a length scale mu squared. The ambiguity in choosing the mu squared corresponds to an ambiguity in defining phi squared. That ambiguity can be fixed in flat space-time, but in curved space-time, that ambiguity can't be fixed. One genuinely has to introduce a length scale in curved space-time to define this operator product expansion. And if one takes the curved space-time that for other reasons one has to do it this way over now back to flat space-time. This is the operator product expansion. That is perfectly analytic at m squared, and in fact, from this point of view, Klein-Gordon theory with negative m squared is a perfectly good theory. It doesn't have a Poincare invariant state, but that's not part of the theory anymore. It has a perfectly good operator product expansion. It has a perfectly good wide class of states. It's an unphysical theory, just like classical Klein-Gordon theory with negative mass squared, because there are instabilities. Classically, you get exponentially growing solutions, and in the quantum theory, you'll have similar unphysical growing behavior of field expectation values, but there's nothing wrong. Just as negative mass squared Klein-Gordon equation is a perfectly good hyperbolic equation with perfectly good deterministic evolution, perfectly good well-posed initial value formulation. Now, in this point of view, negative mass squared Klein-Gordon theory would be a perfectly good quantum field theory. It just doesn't have a preferred vacuum. It doesn't have a Poincare invariant vacuum state in flat space-time. So it would be interesting then, I think, to base the formulation, the perturbative type calculations of quantum field theory on the operator product expansion coefficients, and very recently Hollins and also Hollins in collaboration with Obermann have made quite a bit of progress, which I think Stefan will be talking about in a couple of hours, to developing perturbative rules that would enable one to directly compute in perturbation theory operator product expansion coefficients. When this machinery is more developed, I think it would be very interesting to re-examine the convergence issues within this framework. So thank you very much.
You insisted that your field theory be either renormalizable or asymptotically free, but I don't quite see why that plays a crucial role for the existence of an operator product.
Oh, yeah, no, okay, so I was, in a general theory that is not renormalizable or asymptotically free, I would expect that, I would think one would not normally expect an operator product expansion to exist. I may have worded this badly, but I'm not, it's not.
Theories, for instance, in 2 dimensions where they are quite well known, which don't satisfy either of that, and they obviously have a good operator product expansion.
Okay, so an operator product expansion of this kind of type, I mean.
Yes, they do.
Oh, okay. Well then, I mean, no, it's not.
Large anomalous dimensions, you might say.
Okay, well we should talk further about that. I mean, so no, I'm not using that I'm not using renormalizability or asymptotically free or anything like that in any way. I was just cautioning that at least an operator product expansion of the type we were considering and satisfying the properties that we're considering, and I should find out more about what these properties are. I was cautioning that one shouldn't necessarily expect that to exist. That was all that my remark was intended to be. But again, we should talk further.
Okay, another question. What in your axiomatic setting guarantees that there is any state of the
Oh no, I mean we've just pushed all the difficulties off into, I mean, nothing at the moment. I mean, well, I mean, yeah, so I mean, the way I've presented it, it might seem, kind of, but, right, I mean, that would be a major issue. We have absolutely nothing. If we wrote down this infinite sequence of operator product expansion coefficients and verified that they satisfy all the conditions that we're imposing, at that point we would have absolutely no guarantee that there are any states. So That's clearly a major shortcoming, which, however, for the moment, we've just pushed off to the side.
Another question up here.
Can you also say when two theories are in some sense equivalent? Since your algebras don't carry information and sometimes there are no states whatsoever, it might be hard to detect by some invariant that your theories are really not the same.
Well, I mean, for the operator product expansion coefficients, I mean, you can, of course, do field redefinitions and make those look the two theories from this point of view would be the same if they had the same operator product expansion coefficients. However, it wouldn't necessarily be obvious if you gave me, a list of two different looking operator product expansion coefficients, whether the theories might still in fact be the same. There might be some field redefinitions that make them equivalent. I'm not sure if I'm...
Can you somehow detect that they are really different, or are there invariants that tell that they are really can't be made the same by some real conditions? And then there were theorems about the PCT and do they say that they are really equivalent, or do they just say that they have the same algebras in the same state? Because that might not be enough then to say that they're really the same theory.
Well, I think it's clear the notion that they're the same theory if they have the same operator product expansion coefficients, but of course you have field I think that's a clear concept that there isn't any ambiguity on. Telling in practice whether they're the same theory might be extremely difficult. Again, I'm not sure. The information in the theory in this viewpoint is in the operator product expansion coefficients, and but telling whether two theories are differing from each other just by field redefinitions and they're really the same theory wouldn't be an easy thing to do. In general relativity, if I give you two, the same metric written in completely different coordinates, it won't be very easy for you to tell whether they're the same. If your question is there some invariance that could be calculated that would immediately tell you that they're different, yeah, that might be. That's not something that's certainly not something I've thought of. So I can't give you an answer, but there might be some easy checks that would show that two theories are not equivalent.
One more question?
One remark regarding asymptotic theories. Of course, no dimensions that number of conformal theories which have perfect CPEs, which are preserved under scaling, so they reproduce themselves asymptotically, but you would call them asymptotically free, right?
Yeah, so what's...
So OPEs can very well exist if
yeah.
the theory is not asymptotic.
Right. So I'm very much regretting having made that remark, which was just a cautionary remark that this might... All I was trying to indicate was that this might, if one is putting OPEs as a fundamental status, that might restrict the class of things that one otherwise would have called quantum field theories. But as I say, I'm regretting having formulated that idea of you wouldn't necessarily expect asymptotically free or non-renormalizable theories to have this sort of operator product expansion.
Maybe we better cut off the questions there and thank our speaker again.